Hello everyone, I'm Shagnik and I will be chairing the session and welcome. So it's still 5 minutes till we start. Um, so this is the second public talk for today, and we have Professor Bulbul Chakraborty with us. So please hold on for a little bit longer, and we will start right at 6, and maybe 2 minutes after 6 because the participants are still sharply rising. And try to keep yourself muted. Yeah. Um, Good evening, everyone from India who are in the Indian time zone. And it's already 6, so I would wait another 2 to 3 minutes as the number of people are still joining us. So let's wait for another 2 to 3 minutes and then start with this session right away. So, hello everyone and good evening. Thanks for joining us, and also thank you. This is our second session today, and this is the second public talk we are having today. And today we are delighted to have Professor Bulbul Chakraborty with us, who is joining us from US, which is of course a different time zone right now. And so before I, I I asked Professor Ornavo Chakraborty to introduce our speaker today. I would request all of the participants to try keeping their audio muted and their video off as well, because we want to save some bandwidth for everyone. And also, we are streaming this talk live in YouTube. And as for questions, we generally take questions at the end of the talk. So if you even have questions during the talk, please raise your hand or write the question in the chat box. And either at the end you can unmute yourself and ask the question, or I can read the questions for you to our speaker. And with that note, I would like to please request Professor Ornavo Chakraborty to introduce our speaker today.
Thank you, Shagnik. I think I'm audible. So
Yeah, you are.
thank you very much. And the organizers of Presision, thank you all for asking me to do this job. It's a pleasure and honor for me to introduce Professor Bulbul Chakraborty, who is Enid and Knight Council Professor of Physics in Brandeis University, US. Professor Bulbul Chakraborty is a condensed matter theorist, basically, who is interested in systems far from equilibrium. She began her physics career from IIT Kharagpur in India, and since then she has traveled a long way in science, definitely, and earned a lot of recognition all over the world. Traveled a long way, really, and visited various laboratories all over the globe. For example, beginning with IISc Bangalore and then Argonne National Lab, Yale University, to name a few. And she is an elected fellow of the American Physical Society, and she has also won a Simons Fellowship. And in Brandeis, she is in Brandeis since 1989, I see, and currently since 2006, she is the Enid Annette Ansel Professor of Physics. Professor Chakraborty has a current interest in understanding the response of granular materials to external stresses. This is a very a beautiful area and is something which, to my mind, is not understandable easily. So I'm looking forward to a very exciting talk. And as I can see, Professor Chakraborty has established a theoretical framework to understand the unusual response of these systems, the granular systems such as sand or even dense suspensions. So, with this brief introduction, I think we are all curious to know what Professor Chakraborty has to tell us this evening. So, I now hand over the session to Professor Bulbul Chakraborty from Brandeis University, US, to talk about the subject of her interest in this precision event. Professor Chakraborty, please.
Thank you very much. And I want to thank the organizers for giving me this opportunity. This is actually the first time I'm ever speaking at Presidency, even though this is virtually. And I hope you're all doing well in the city of my childhood, in the midst of these weird times and the pandemic. Shubho Shandha. So let me begin. I'll share screen and so I'm going to actually start without trying to explain in words what fascinates me and why sand as a substance, as a material, is so puzzling. I'm going to start with a video. And the video is taken at Brandeis a few years ago of students playing, essentially playing in a lab in borrowed space. I don't have a lab since I'm a theorist. Um, and let's start with that and see how it goes. You can move it to the floor. Yes. Okay. So this is actually a perfect stick. What you always put your hand underneath the Okay, so here is something that you probably saw that should surprise you. So what you saw was a material that solidified not by changing its density or its temperature, but by gently tapping it. So you gently tap this material, um, and it became a solid. Edwin, this student, undergraduate student who was working with me then, could pick it up with this stick. My uh, my favorite colleague, Bob Berenger, used to be brave enough to actually put a chain inside this and twirl it around. So really becomes a solid. But then what you saw was these materials, even when they're a solid, are fragile. Like little taps can completely distort the structure inside and make them fall apart. So that's what you saw at the end of the video. So this is something that we created in the lab. This is sort of a demonstration of what sand does, which as a condensed matter system is puzzling. But if you think about what we see around us, our natural landscapes, what you saw in the lab is a tiny bit of what's happening there daily. So our natural landscapes are made out of boulders and rocks and gravel. And what happens is that small perturbations, like our taps, they compress these materials, but stresses build up inside this. And because of the lack of thermal fluctuations, which I will come back to again in a minute, because of the lack of thermal fluctuations, these external perturbations, shear, wind, us walking on something, these stresses build up, but then there is a failure point for these materials. And that failure then occurs abruptly because thermal fluctuations don't smooth them out. And that's what leads to earthquakes and avalanches and catastrophic phenomena that we think are not predictable. So, what I have been fascinated by for the last decade is trying to come up with a condensed matter or a statistical mechanics paradigm to understand these kinds of systems. So, that's what I'm going to try and share with you today. And I begin with showing you my collaborators. So the journey actually started with my then student Silke Henkes, who got her PhD in 2009, continued with a bunch of students, postdocs, and then most recently a collaboration with Shubhra Bhattacharya at ICTS in Bangalore. And this work would not have been possible without my collaboration with Bob Berenger of Duke University, who passed away a couple of years ago, just all of a sudden. But Bob really led me through granular physics and taught me all about it. And then I have this collaboration with Jeff Morris on trying to understand suspensions. Okay, so here are again, just to get you excited, and these are some of the things that you probably have seen, wondered about, maybe puzzled over. But so these pictures are again trying to illustrate for you some of the weird features of sand-like material. So on the top left corner here, you see that around this leopard or cheetah, the leopard is walking, but around it, the sand is flowing. Around its feet, the sand is flowing. So this is something that you probably also observe if you walk up a sand dune. The sand dune is able to support your weight, you're walking, but the sand does flow around your feet. So it's a weird substance that we cannot really categorize it's a weird state that we cannot really categorize as a solid or a liquid or a gas. But really, is it that bad? That's what it's probably not, is what I would hope to convince you. The left bottom picture is something that you might have observed when you're walking on a beach and you have a little bit of water in the sand, so you're near the water's edge. And then what you observe, if you can see it here, is that around your feet, the sand gets dry. And at the end of the talk, so think about why that might happen. And at the end of the talk, I might ask why you think that happens, or we can talk about it. Mixing of sand is a weird phenomenon. Normally things mix if you shake them, but sand often segregates. Sand-like material often segregates if you try to shake them up. So these are the kinds of puzzling physical observations that we would like to try and understand. But as a theoretical physicist, a condensed matter physicist, I'm going to focus on some well-characterized phenomena in these materials that we have been trying to understand. Okay, so I begin with showing you this video, which was sort of the beginning of my journey with Bob Berenger, because it helped me look inside sand. So what this material is, it's sand in the sense that these are macroscopic particles. These are millimeter-sized particles. what you're looking at, gravity is not this way, gravity is that way. These are particles that are sitting on an apparatus on the top of a table. So gravity is not acting this way. So you can sort of ignore gravity because it's the same for all of the particles. These particles are made out of photoelastic material. And photoelasticity is this property that some of you might know, some of you might not, is that if you apply stress on it, the material becomes birefringent. What that means is that different polarizations travel at different speeds. So what the experimental setup here is that you see, hopefully you see that some parts of these are bright and some parts are dark. So the parts that are bright are where there are stresses already existing, and the parts that are dark, basically there are no stresses. So what I want you to take away from this image is, if I did not look through these or if Bob Berenger didn't look through this polarizer to identify where these stresses are, just by looking at the positions of these particles, we would not pick up any difference between, let's say, this part and this part where there are no stresses and stresses. So keep that in mind, and I'm going to play this video for you, and what you're going to see is these stresses developing in sort of filamentary structures, which are called force chains. So what, if I can run it one more time, maybe I can, yeah. Or I can go back and let me just play it. So what you're seeing here is this material is being sheared. It's the box shape is basically, within which the material lies, is basically being distorted. And what you see is, as the grains are sort of just moving along with the box, they're just there for the ride. But for the small changes in positions of the grains, the forces change by large amounts, and this whole structure then develops. And this is one of the phenomena that we studied, and I'm not going to talk about it very much today, but what happens at the end of the video, this structure now actually behaves like a solid, in the sense that if I try to shear it in the reverse direction, it can actually support the shear. Whereas if I try to do it here, and if I try to reverse the shear at this point in time, then it would not be able to. So this kind of strange behavior is what we are trying to understand. And by looking inside, what I mean is, we're actually, what we need to understand about, to understand sand, we have to get away from this picture that positions of particles and their momenta, which forms the basis of statistical mechanics, are not enough. You need to know something else. So that's the change in perspective that actually helped us move forward with understanding this kind of systems. Okay, so what are the kinds of materials that we are interested in? So I want to give you sort of a list of things that that characterize the materials that fall outside this realm of what we normally think of as condensed matter systems. So the collection of macroscopic objects, and what I mean by that is gravity plays a role, and thermal fluctuations, which is the third thing here, does not play a role. So if you imagine putting a pile of sand on the floor or on the desk, and you just leave it there without touching it, with no vibrations around, it'll just stay there, right? So because they're heavy, because they're massive particles, the normal temperature in to have thermal fluctuations play any role at all, the temperatures that we need are astronomical. So that doesn't happen. So these particles are non-Brownian. Most of the systems that we are interested in actually have purely repulsive contact interactions. So this is also a crucial difference to normal systems that we think about, because the systems have no cohesion by themselves. Most systems that we think about as, like, let's say, forming a solid, um, water molecules, even our idealized systems such as hard spheres at finite temperature, there is actually entropic cohesion between them. But because sand, which are in some ways hard particles, very rigid, because there is no temperature, there's nothing to sort of give them cohesion. So they only respond to compression. They have no tensile strength. And that's an extremely singular situation that is responsible for some of their weird behavior. These particles have complicated surface properties. So what you saw in the lab was just sand picked up from a beach. I have no idea, right, what their shapes were, what their roughness was. So to be able to imagine that we can actually characterize the interaction between two particles in detail is sort of a dream. It's almost impossible to do that, because tiny changes in particle positions or which particles we are looking at will change those interactions. So in some ways, we are confronted with a situation where, in addition to the normal statistical behavior of a large collection of particles, there is noise at the particle level. There's noise at the level of where particles are interacting with each other. So we don't have a potential system. We cannot write down a potential. This I have already said a couple of minutes ago. So they're non-ergodic in the extreme sense. If I put a bunch of sand somewhere down, they don't explore phase space. They stay in one configuration unless they're driven by some external forces like me shaking them or the wind blowing over sand, etc. So the only way they explore the states available to them is through external driving or through boundary forces. So then the first response of physicists to this kind of system is we cannot do anything with it. This is all history dependent. This is all, messy. But again, what careful experimentation by physicists starting in the mid-90s established is that even though these systems are not characterizable in our usual thinking, and they have large fluctuations. So if you look at distributions of forces inside a granular material, they have very broad distributions, exponential. They're non-Gaussian most of the time. So there are no thermal or quantum fluctuations. They have broad distributions. So there are fluctuations coming from external driving. But the good thing that came out of these experimentations is that these distributions are reproducible. So if I follow the same kind of protocol, so if we look at the experiments that we did in the lab, in the video, or in Bob Berenger's lab, if I followed exactly the same protocol and measured distribution of stresses, distribution of forces, whatever we want to measure, those distributions are reproducible. So that, to me, makes this a condensed matter system, a StatMech system. I can think about distributions and try to understand what's going on. Okay, so I'm going to focus on two sets of problems, mostly focusing on the second one. But one of the questions that we've been trying to address is transitions in non-equilibrium steady states created by fluid in suspension, so mixtures of fluids and grains, and then stress transmission in static granular assemblies. I can pause just for half a minute to see if there are any questions or anything that I should address at this point, just to give me some context.
Yeah, I see one question by Professor Parthasarathi Majumdar, who
Okay.
says that I seem to see appearance of an order with increasing shear. Is this correct?
Yes, order, not in positions. The positional order doesn't change, but if you have a way of characterizing the force order, it does appear. And I will try to show you some pictures maybe at the end, but you'll see that's the paradigm change that uh, we want, is that we need to think in terms of forces in addition to positions. Okay.
I don't see other questions at this point, I think.
Okay. Okay, so this is the first set of problems in suspensions that I wanted to just present to you and tell you what the challenges are. So these are, again, and also I work extremely closely with experimentalists and numerical experimenters, even though I don't do any of them by itself. So these are experiments that were done in Professor Heinrich Jaeger's lab at Chicago. And what I'm showing you here is measurements of shear stress versus shear rate. And I know physicists are often not familiar with what all of these are, at least not in the US. So let me just point out that if we had a Newtonian fluid, in a Newtonian fluid, the stress increases linearly with the shear rate, and that slope is the viscosity. So the black line here is your reference point. So this is what would happen for a Newtonian fluid. What you're looking at here, the system, is a suspension of cornstarch. So rough particles suspended in a Newtonian fluid. The fluid has nothing strange about it, but you have particles suspended in it. And then these different colors here are denoting increasing packing fraction of the grain. So increasing density of the particles suspended in the fluid. And these are non-Brownian. The particles are large enough, again, because it's cornstarch, that Brownian motion doesn't play a role. So what you should be seeing here is that as you increase the density of the particles, as you make the suspension denser and denser, then you deviate strongly from this Newtonian behavior. And what is really, really striking is, see, this is a log scale. So what you see is that the stress goes up by 2 orders of magnitude for essentially no change in the strain rate. So this has been termed discontinuous shear thickening. And the discontinuous refers to this jump. Actually, you see the jump here. And then in the red curve, you actually start seeing a back bend. So if you think of the reason it's called discontinuous shear thickening is if I now measure the viscosity just by looking at the derivative of sigma to gamma dot, the stress with strain rate, then the viscosity shows this rapid rise. And this is not something that you observe in normal suspensions. So this is a kind of thing that we have been trying to understand. And so I'm going to present this to you in a phase diagram. So again, to get my audience used to the fact that even though these systems are strange and we might use strange access to construct a phase diagram, I still want to put them within our usual constructs of condensed matter or physics or statistical mechanics. So what I'm plotting here is as a function of and this is actually from simulations in 2 dimensions, so the numbers are slightly different, but this is the packing fraction. So this is increasing density of particles in the suspension, the suspended particles in the fluid. And this is the shear stress normalized by some characteristic stress that is actually turns out to be very important, but I don't have time to go into that. And what I'm plotting here for you is a phase boundary. And the phase boundary is marked by looking at this plots of the curves of sigma versus gamma dot, the flow curves, and drawing a locus of points where there's d gamma dot d sigma is 0, which means that sigma changes for an infinitesimal change in gamma dot or no change in gamma dot. So d sigma d gamma dot is infinite. So if you want to connect to something similar that we are familiar with in condensed matter systems or StatMech, this is the inverse of the susceptibility. So along this line, the susceptibility diverges. So here, the questions that we would like to try to answer these are now non-equilibrium steady states, so they're not static, they're flowing, and they have well-defined distributions, so they are actually steady states. And how do we understand this kind of a phase transition? So when I cross over from what is known as continuous shear thickening, where you don't see any of these dramatic rise, to discontinuous shear thickening, and then if you go into this regime, you actually shear jam the system, which means it becomes a complete solid. It cannot flow at all. So just again to sort of tweak your curiosity, and because I'm not going to talk very much about this phase diagram, in the next slide, I'm going to do something that should make you look at this phase diagram with some sense of familiarity. So what I've done is I've just rotated this phase diagram 90 degrees. And does this remind anyone of anything? So if I replace the sigma here by density and this by temperature, this is not quite, but if this thing hadn't, if this blue curve wasn't there, and if this red curve came down, this is a van der Waals phase diagram, right? So this is TC in that picture. So above here, I have a homogeneous system, and then I have two-phase coexistence below this in a normal van der Waals picture. So this is then intriguing, and the question we really want to try and address is, can these non-equilibrium, non-thermal systems be put into these kinds of existing framework of a phase transition? And what then characterizes these phase transitions? Is this a diverging length scale? Is there a diverging time scale? What happens at these points? So these are the kinds of questions that we are interested in. So I'm going to just leave, I think I'm leaving the suspension problem here, and I'll come back to it towards the end. And I want to show you another set of problems that I will focus on mostly from now on. So this is response. So the non-equilibrium steady states, because they're flowing states, are, as you can imagine, more difficult to understand than static assemblies of grains. So we are starting from trying to completely characterize the behavior of static systems, such as a sand pile or systems like that, and then move on to the dynamics. So in the static systems, a long-standing problem, you see these images are from a Fitzgerald letter in 2001 from Bob Berenger's group. There's this long-standing question of why and why do the stresses get transmitted in a very inhomogeneous way? So I'm going to lead you through these pictures. So this picture up here, and now gravity is actually in this direction. So what you see is that there is and it's two dimensions. So there is basically no third dimension here. So I have a 2D infinite system, semi-infinite system under gravity, if you want to think about it that way. And you see these structures that have developed due to gravity, because the weight of the grains are of the one layer are exerting forces on the next layer, etc., etc. And as you can imagine, the stresses becomes larger as you go towards the bottom of the pile. So starting from that system, then what is being shown in this picture is there is a small force applied on one of the grains on the top. So this was the as prepared sample, and this here now is measuring the response of that to a small perturbation. And the small perturbation then creates these sort of tree-like or wave-like structures, if you want to think about it that way. And this picture then is the response. So this image has been subtracted from that image. And then you do see this response has this characteristic like river flow kind of structure. This is the same thing, just repeated another time. And what you see is there's variation. So what I'm trying to get to here is that there is not just fluctuations of the stress within a sample, there's large sample to sample fluctuation. So we do really need to try and understand what's going on here to have a predictive theory. And bottom here, what we are showing, what is again taken from these experimentalists, is just ensemble average. So now ensemble averaging these patterns. The ensemble average pattern from these images looks like that. And then what Bob Behringer did was change the way this system was constructed. So this one was made out of rough grains. This one was made out of this is a crystalline arrangement of grains. This is a disordered arrangement of grains. So anyway, without going into details, you see that the way our packing is prepared can influence this ensemble average responses. Okay, so I'm going to show you in my talk today that there is an analogy between these force chains and charge propagation in a kind of electromagnetic system, which is a generalization of our normal ENM to vector charges. So the charges in this theory are not scalars, but vectors. And that automatically then gives an explanation for why you have these chain-like propagation of the stress. So wait for that. That's what we are going to get to. And what this ensemble average, what we think, or the way we are understanding it now, is that granular material, again, so I'm going to present you with an ENM-like structure for stress response in granular materials. So even though that sounds weird, bear with me, that's what was going to come up. But granular materials they're not like ENM in a vacuum. They are actually polarizable. So you have to think of them as a dielectric material. And then our understanding so far of these different responses is just that if you create networks that are different, they have different polarizability. And if their polarizability is different, then we know from standard ENM that their response is going to be different. So that's what I'm giving you a taste of what's going to come, what has happened, what this my decade-long investigation, I think we're finally at a point where I think we do have some, the beginnings of a complete theoretical framework. Okay, so how do we think about these systems, right? So we have these rough particles. As I said, I don't really know what the microscopic interaction. So we have to change our perspective. And we always beg, borrow, and steal. So this is nothing new. This is a perspective that has existed in condensed matter systems, not completely well disseminated because it has lived within the context of small communities, mostly in quantum condensed matter physics. So the way to think about these systems is we actually don't want to try and understand what happens at every particle level. That's sort of a self-defeating quest. It's not going to work. we want to take a different approach to this. And the approach we want to take is that the collective behavior of these systems is completely controlled by the constraints that are put on them, the local and global constraints. So remember, there are no thermal fluctuations here. And so the system is completely non-ergodic. So, and they are in mechanical equilibrium. So every grain has to satisfy the constraints of local force and torque balance. So we are doing Newtonian mechanics at the most, there's nothing but Newtonian dynamics in here, but we are looking at Newtonian dynamics in all its complexity with friction, with adhesion, cohesion, whatever at the particle level. So we want to take this broad perspective of saying, oh, but I do know what the constraints are on this system. For every configuration that was created in that earlier slide, even under the response, the system is static. So you put a force on it, you wait until the system becomes static again, and you measure the forces. So in all of these configurations, every grain is in force and torque balance. Every grain is in force and torque balance. I have imposed global stresses on the boundaries. So the stresses have to add up to the stresses that I have imposed on the boundary. There are all kinds of complications coming from the fact that there might be lubrication forces, there might be frictional forces. And then I have these two weird conditions, not weird, but difficult constraints to take into account in a statistical mechanics context, which is that I have the static friction law, that for a system to be in static equilibrium, the tangential forces have to be less than or equal to some friction coefficient times the normal force. And the other thing that I mentioned at the beginning, that all these normal forces have to be positive. So highly constrained but highly degenerate is the way we want to characterize the system. How am I doing with time? Am I over?
No, I think
How many
you're
minutes
good.
do I have?
So I think it took about half an hour at this point.
Okay.
Half an hour.
Okay,
So
good.
we have a lot of
Okay.
time.
Okay, thank you. So think of these systems as highly constrained but highly degenerate. And and what I mean by that is, if you ask what are the microscopic configurations that satisfy all of these constraints for a given set of, let's say, global stresses, there are many of them. There are exponentially large number of them. So it's not that and that's why there are fluctuations. So even if I fix all of the external stresses, I still have many configurations that are consistent with those and still satisfy all of these local constraints that I'm specifying here. So what is the theoretical challenge? So now I'm really going to dive into trying to construct a theory. What is the theoretical challenge? So I'm going to quote from someone. So a fundamental problem in handling such systems theoretically is that of navigation among these states. Is there a way to label and enumerate the states so as to carry out a sum over them and evaluate a partition function? That's what we want to do, right? Or if a particular state is somehow to be selected out of the ensemble, how do we find that needle in a haystack? So what the author of this, which will be revealed in a second, is asking is, suppose let's say in the suspension problem, we saw that we had a phase transition. All of the states in this phase diagram anywhere all satisfied these constraints of local force and torque balance and satisfying the global stress constraints, any other constraints that I specified in the previous slide. So what is it that when we change the shear rate or the shear stress, what determines which states are chosen? Because we must be choosing a certain certain set of states for the collective behavior to change. So how are they selected out of this ensemble? So that's the question. Now here is the reveal. This was a quote from Chris Henley talking about Coulomb phases of frustrated magnets. And what I claim is that these two systems are not very different. The same challenges and the same approach uh, can lead to the construction of a theoretical framework. So here is what is known, and I will, in the next slide, I'm actually going to give you a very, very quick overview of what has been done in these Coulomb phases of frustrated magnets to give you a context. And if we understand that system, then really the granular problem is just a more messy version of that. So what was known in the Coulomb phases problem is that you can construct a coarse grained description by identifying the right kind of conserved quantities. And I put conserved within quotation marks here because it's not the usual kind of energy conservation or momentum conservation. But what Chris and Henley pointed out beautifully in this review article from which I'm quoting is that constraints lead to conserved quantities. And then you can coarse grain based on those conserved quantities that have now been identified. So let me see if I can illustrate that with a very simple example. So what I'm showing you here are the ground states. So this Coulomb phase of frustrated magnets, a classic example, are the ground states of the triangular lattice Ising antiferromagnet. I'm assuming most people are slightly familiar with what that means, but here is just one triangle of my triangular lattice where I'm trying to show what the spin configuration. So it's Ising spin, they can be up or down. And the reason it's frustrated, right, is that these are antiferromagnetic. So if I put a spin down here, this spin wants to be up, this spin wants to be down, and there's no way I can satisfy the energetic demand of this bond. So this bond is unsatisfied. So what we see here is an illustration of a classic frustrated system. Does that make sense? So in the ground state of the triangular lattice Ising antiferromagnet, the best that we can achieve is that only one bond of a triangle is unsatisfied. So if this one bond is unsatisfied, so I can come up with any configuration of these spins with the constraint that every triangle can have at the most one bond where the two spins are pointing in the same direction. So if we keep that in mind, I can go to a different representation. And that representation is a dimer covering of the dual lattice, the honeycomb lattice. So what I have done here is, if you remember the bond that was bad was this horizontal bond. So this vertical bond on my honeycomb representation now bears two arrows pointing up towards this vertex. The two bonds that were satisfied now have these arrows that are going out from the vertex, but a single arrow, right? So that's just a convention mapping from the spin configuration to these arrow configuration on the honeycomb lattice. So this is a one-to-one map. There's no, it's unique. But now I can actually go to bat trying to construct a StatMech framework. How? Because I can think of these as lattice fluxes. So at each vertex, the constraint that the ground states of the triangular Ising antiferromagnet have to satisfy is translated to the zero flux at every vertex. So I have two flowing in, one flowing out, one flowing out. So the total flux the lattice fluxes add up to zero at every vertex. So my constraints don't allow me to put two arrows here. But I can come up with many, many, many different configurations that will do that. So for example, in this kind of system, I can just clockwise rotate these arrows. So this becomes two, this becomes one, And you can convince yourself that still satisfies the constraints. So there are excitations that do not violate the constraint, and many, many, many excitations like that. Two more really important features of these systems. So what I just talked about is the many microscopic configurations give the same total flux. So the total flux in this system on the left-hand side is 0. If I look, let's say, in some direction. So if I look in the vertical direction, the total flux is 0. So 2 going up, 1 coming down. If you add all of the bonds up, the total flux is 0. The total flux here is maximal. But even more important than that, this total flux, row by row, is conserved, right? So if I look at this row and sum up the total flux, that has to be exactly the same as the one up there. So there is flux conservation that emerges from the constraints. So the conserved quantity now is the flux. So that immediately tells us that we should think of a Gauss's law, right? So I have E and M, divergence of E is 0. And then from that, the Coulomb phases of frustrated magnets can be understood just by writing down a usual Lagrangian, a usual E and M Lagrangian, and solving it with the usual kind of introducing a gauge potential. Let me pause just for a second again, just to see if there's
Yeah.
anything that I can.
I think there was a previous question from Professor Bulbul Chakraborty, which was if we wish to do an experiment with such a
Yeah.
system, do we need to have any threshold for the thickness for such a system? Or do these happen if we have a two-dimensional system?
So, right. So I'm assuming the question is when I said it's a 2D system.
Yeah.
Okay. So, of course, it's not infinitely thin. The reason these experiments are done in 2 dimensions, the phenomena we believe extends to 3D. But these kind of photoelastic experiments that I was showing you from Bob Behringer's lab can only be done in 2D because these materials are not transparent. So you cannot do the imaging in 3D. Does that answer your question?
Uh, yeah.
So
It says
2D
yes.
doesn't mean strictly 2D. Of course, there's a grain diameter in this direction, but it's one layer if you want to think of it that way.
Yeah. And we had another question, which is from Onuran Kargupta. He says that how are the images of the responses produced?
The same way as so let me go back to these pictures.
Yeah.
So again, it's the same photoelastic material is what I should have said that. It's the same technique that I showed in that video earlier. So these are again photoelastic images. So the way these are done is there's light shining from the back, and then there are polarizer plates in front, and the imaging is done through the polarizer plates. And then it picks up wherever there is the bright region, and then there is false coloring, etc. So then wherever these bright regions are where the stresses are high. And so so that's basically it. But what is really neat is these experimenters can actually now go and analyze these images and really produce for us forces at every contact, including the normal and tangential forces. So that's a big step to trying to understand the systems.
Yeah. So I would like to have another question, and then I think there are other questions too, but we can address them at the end.
Okay, sure.
So the last question right now is by Shayonil Molla, who says that since we're talking about the experimental setup, he says that can you tell us that how the perturbations are created, like in an experimental setup?
Oh, in that same
Right.
so the perturbation. So essentially, these are macroscopic particles, right? So they have like a tiny probe, and they just push on the particle at the top just a little bit, and they have a. trying to remember. They have a gauge for measuring how much, but it's really a tiny, tiny force. But what they make sure of is they're pushing on just one grain. Does that make sense?
Yeah, that makes
Okay.
sense. So we have many other exciting questions right now, but we
Okay,
will
but we
address
can.
them at the end. Yeah, yeah, and you can
Okay,
continue.
thank you.
Yeah,
Okay.
yeah.
Okay, so this is the approach that then we want to take over to our granular system and see how far we can go with that. So let me reiterate for you what the constraints are. So the global stress tensor imposed externally is like the total flux in my previous system. So that total flux is something that we control. Local force and torque balance satisfied for every grain is this the lattice, like the lattice flux is adding up to zero. I should make sure that I want to ensure that I don't make you guys think that the problem that we are going to look at now is a lattice problem. It's not, right? So we don't, it's much more complicated than the previous problem. But in a coarse grained sense, just like we had divergence of E equal to zero, we know in mechanical equilibrium that the divergence of the stress tensor is zero. So let's think of that as our Gauss's law. Also, so local force balance translates to this Gauss's law. Divergence of stress tensor is zero, right? This is momentum conservation. I just want to make sure. So otherwise, divergence of sigma would be the change in momentum. So the divergence of stress tensor is zero is just telling me I have the static equilibrium condition. Torque balance, which we normally, so anyone who's done fluid mechanics or continuum mechanics will know, but again, we don't emphasize this enough in physics education. Torque balance ensures that the stress tensor is a symmetric tensor. So if I look at a grain level stress, if I measure the stresses on every grain, at every grain, the stress tensor has to be divergence free. And what I mean by a divergence here is some discrete analog of the divergence operator, because I have these things sitting in some network, and sigma has to be a symmetric tensor. So what our expectation is that once we coarse grain properly, just following sort of the same ideas that we had in the Coulomb frustrated magnet problem, Coulomb phase, if we coarse grain properly, these should be the equations that emerge. So this is Gauss's law for the granular problem. So what are we after? We are after a theoretical framework that is starting, whose starting point are these equations. So now what is the problem? Why can't we just stop here? So divergence of stress is zero, sigma is a symmetric tensor. That just comes from the local force and torque balance. So what is the problem? The problem is, do we have enough equations? And the answer is no. So let's think about it. Let's think about it in 2 dimensions. So in 2 dimensions, the stress tensor has 4 elements, sigma, let's say sigma xx, sigma yy, sigma xy, sigma yx. It's symmetric, so I have 3 independent elements, but I have only 2 equations. So I don't have enough equations. So normal elasticity theory, the missing equations are the constitutive equations. So they're not part of any fundamental conservation principle. They are the constitutive relations that describe a material. So in elasticity theory, these constitutive relations are the stress-strain relations. The elastic modulus tensor defines a relation between stress and strain. That relationship then gives us the closing equations. And that relationship in normal elasticity theory is derived from a free energy. So we don't have that here. So that's how we get around this problem in normal thermal solids, normal solids, which are derivable from a free energy framework. But here, we don't have that crutch, so we don't have enough equations. And this problem has been in the granular community for decades and has been posed as, can we come up with a stress-only description of stress transmission in granular materials? We don't have the definition of a strain field. And I can say a little bit more about that at the end of those questions, but it might be intuitively clear that in these granular materials, there's no reference structure, no displacement field, and no strain tensor that I can define. So in the absence of that, the question is, can we come up with another equation that lets me close the problem? And the answer is, if I put forward the hypothesis that the reason we have these equations is there is an underlying gauge theory, there's an underlying E&M problem, then it helps me close the construct a theoretical framework. So let's see if that works. So again, as I said, we always beg, borrow, or steal. So it turns out, and this is how my collaboration with Shubhro developed. I was giving a talk at ICTS, and Shubhro said, but Bulbul, do you know about this tensor gauge theory from Michael Pretka? And I said, no. So in the context of quantum spin systems, a theory had been developed, which is called the theory of fractons, which is an E&M theory generalized to rank two symmetric tensors. So it's a U1 gauge theory, but it's not a theory. The E field and the B field and the vector potential, the A, are not vectors anymore. They are symmetric tensors. Now, there are two versions of this theory, or the two separate kinds, both having this feature that the E and B are symmetric tensors. One has a vectorial charges and the other has scalar charges. So the one that can apply to the granular system is the one with vectorial charges. So that's the one that has this Gauss's law. So this is a tensor. So if I wrote it as Gauss's law with a charge sitting on the right-hand side, the charge would have to be a vector. Okay, so what does that tell us? So again, conservation laws, right? We fall back on things that we know are fundamental and robust, and we want to build on that. So what are the conservation laws? Again, I'm glossing over or giving you just summaries of things. So the two conservation laws that emerge from this Gauss's law, the fact that I have a symmetric tensor and I have a divergence of the tensor being 0, is that charge and charge angular momentum are both conserved. So force is conserved and torque is conserved in the granular context. Now, the reason these things are called fractons is the fact that if charge and charge angular momentum are both conserved, then since the charge is a vector here, the charge is not just a scalar, it's pointing in some direction. If I put a charge in this direction, in vacuum, that can only propagate in that direction. It cannot deviate. So even in 3 dimensions, I have one-dimensional propagation, one-dimensional excitations. So because these are the subdimensional excitations, they have been called fractons. And what we've been able to show pretty conclusively is that it is this propagation of vectorial charges in a dielectric medium that visually shows up as force chains in granular materials. So that's the picture. But now, how does this gauge theory help us solve this, close these equations? And the answer is pretty simple. We have the full set of Maxwell's equations. We don't have just Gauss's law. We have Ampere's law and Faraday's law. So now in the static condition, so it's interesting that in this E&M, to solve for the electrostatic problem, we actually need to bring in Faraday's law. That's not true in usual E&M, but here it is, and this is something, a point that was emphasized by Michael Pretka. Just for the students out there, Michael Pretka was a graduate student with Senthil at Harvard when he came up with this theory. So you guys get working there. Okay, so now if we say that there is a Faraday's law and Ampere's law in it, like we have the full set of Maxwell's equation. Then the static condition becomes, since the derivative del B del T is zero, the curl of E is zero, but the curl of E here is a double curl because it's a tensor. But those are details. But now I have more than enough equations to solve for the stresses in my granular media. So the point is that this missing equation that had plagued us for many years now comes about as a consequence of this underlying gauge invariance and gauge theory. Interestingly, it also turns out that the structure of this ENM theory looks very much like standard elasticity theory if we allow ourselves the possibility that the displacement fields that we think about for crystals or in normal elasticity theory become gauge potentials in this theory. So that's a very, very appealing picture. What it's saying is that for systems with no broken symmetry, which are most of our granular systems here, they have no underlying order. In those systems, there's a gauge potential which plays the same role as a physical displacement field in a broken symmetry system. The difference is here, it's not a physically realizable field. It's just a gauge potential. There's no way I can measure it. The only things I can measure are the stresses in a static media, which are the E fields. So that's basically the end of my story. I'm just going to show you I'm going to end with this illustration of how the theory works. So the paper just came out yesterday in Fitzgerald Letters. And what I'm showing you here are comparisons of stress correlations. So again, the point is we have to ask the right questions. So just like in any gauge theory, the only things that I can measure, I have access to, are correlations of the gauge invariant objects. So I can't ask about forces, or I can't ask about displacement fields, but I can ask about stress-stress correlations. And so if you measure the stress, so these are measurements of stress-stress correlations in experiments, and it's remarkable. There's this dramatic or singularity kind structure, which is called the pinch point singularity, which emerges just from the structure of ENM. There's nothing more to it, just the Gauss's law and the symmetric stress tensor. So now so that comes very naturally. The material properties, as I said before, shows up as sort of a polarizability of the medium and appears actually as an effective elastic modulus. So that said, what I just want to show you is that the theory works. So the black lines here are the theoretical predictions, and the red dots are actual experiments. And there's no adjustable parameter. All we do is scale the peak height to 1 for one of these stress-stress correlations just to get, because I have no way in the theory of saying what the stress scale is, what the characteristic force is. And what I was saying before is these force chains are nothing but a reflection of these stress-stress correlations. This anisotropy, that the correlations of, let's say, the x component of the stress tensor is predominant, and this is in Q space, but those are all details, are much, much longer range. So what we are picking up as force chains is the fact that these stress tensor has a weird correlation. The correlations are long-ranged and positive in the longitudinal direction. So for sigma xx, the correlations are long-ranged and positive along the x direction. They are long-ranged but oscillating and negative in the y direction. So that's what we pick up as force chains. So here, these are grains colored by the x component of the stress. And you see that they seem to be propagating forever in the x direction. In the y direction, the correlations are negative. So the stresses, if they're high here, they drop off. Same way, if I color them by sigma yy, the correlations are essentially the positive and long range in the y direction, but they decay in the x direction. So we understand this as just a feature of these vectorial charges. So let me end here because I think I have thrown a lot of concepts at you, and I will be happy to take questions. The bottom line, I think, the message that I want you to take from here is we can understand, we can think of these systems as part of the condensed matter framework as long as we are willing to look at it from a slightly different perspective. And this mapping of something that seems so mundane, things that we are walking upon, the mapping of the theory of that to a kind of electromagnetism, a gauge theory, is dramatic maybe, but it's also one of the things that we know in physics. There are only two kinds of things we can have. We can have interesting things coming from broken symmetry, or we can have interesting things coming from a gauge theory. So I think that's my message, and let me end there and stop sharing screen for now and take some questions.
Thank you, Professor Chakraborty, for the wonderful talk. I thoroughly enjoyed it. And so let me just go back to some of the backlog questions we had earlier, and we have many questions as of now. So I will get quickly to them. So the first one was from Professor Bulbul Chakraborty again, and he asked that do these force trees have any multifractal behavior? They look like fractals.
That's an interesting question. To answer that, Orunabo, my current understanding is that whether it's a multifractal or not, that crucially depends on the underlying network property. So the theory that I've presented glosses over the effects of the underlying contact network. We have incorporated it just by saying, oh, this underlying contact network in some coarse-grained way provides elastic moduli. But if we really want to know how these force chains bifurcate and propagate, we need to know the network. And interestingly, if you coarse-grain that picture, you emerge with the same kind of ENM. But if you look at very particular networks, I think there will be some very nice structures to how this forces propagate, right? So in my language, in the ENM language now, it's asking if I put a charge in this direction, and the charge can create dipoles, that's my polarizability, but it can create dipoles only in certain directions, only along the existing network edges, then it can give me a fractal structure, but that's more a property of the underlying network. Does that make sense?
So we will be waiting for Professor's response, and then moving on to a live question, and then I will read another question. So Doipayan, I see, had raised his hand, so please Doipayan, unmute yourself and ask your question.
Yeah, hello Shagnida, am I audible?
Yeah, you are. Yeah.
Okay, so ma'am, thanks for the great talk. So my question is that do we expect an analog of current if we extend the paradigm to moving systems and a conservation of charge?
Absolutely, yes. So we are trying to so what this current is, right? So again, you'll have an electric charge because a current if the charge is flowing. We don't have so we have the full set of Maxwell's equation. So what we need to do is identify what the B field is and what the currents are in these granular systems. And we don't have a complete answer yet. But there is no mystery to where they could be coming from. We are basically taking Newton's equations and translating them into an E&M language. So we should be able to figure out what this current is. So far, we have written it down, but it just has too many terms in it. Does that make sense? There is a current. And in the suspensions, we actually need to incorporate that current to understand what's going on.
Yeah, thanks a lot.
Okay.
So moving on to another question from Parthasarathi Majumdar sir. He says that in any theory with Lorentz and translation invariance, the two conservation laws you mentioned emerge naturally from these symmetries. The conservation of the stress tensor from translation invariance and its symmetric property from angular momentum conservation. So I think it's more of a comment. So yeah, if you want to
but let me respond to that. There is actually no Lorentz invariance in this theory. So you actually have to work a bit to start from the to construct the Lagrangian with the constraints, because this system has no Lorentz invariance. And this has been
can I interrupt you, Bulbul, for a second? This is Partha.
Yeah. Yes.
So, but is there a rotational invariance of some sort?
There's rotational invariance, yes.
So that would do the job. Yeah.
Yeah.
You don't need special relativity. If you have rotational invariance, it does the job.
So we certainly have translational invariance and rotational invariance, and these conservation laws just emerge from that. There's no argument about it. All I was saying is, if I want to start from a Lagrangian, we have to be a little more careful. Because
I think the point is that rather than think of an E&M, you could think of a much larger class of theories which have these properties.
Okay, maybe we can exchange emails and understand what you're saying. But yes, if you have symmetric tensors and you have rotation and translational invariance, these two conservation laws will just emerge. Is that what you're saying? Sort of?
Basically. So that would be the underlying structure on which you can build other classes of theories.
Yeah, absolutely. Yeah. But yeah, send me an email. We should talk.
Very nice talk.
Thank you.
Yeah, thank you, sir. And there's another question from Moitreo, who says that you said that the polarizability depends on the protocol. So could you please elaborate on what these protocols are?
So the most important part of the protocol is the kinds of underlying contact networks they create. So really the polarizability is heavily dependent upon what kinds of dipoles can be created on the existing network. And so if the network is crystalline, for example, then I can create, the polarizability will have some certain symmetry properties. Whereas if the network is completely disordered, the polarizability tensor will lack symmetry properties. I should have said one thing, that this polarizability tensor acts as an effective elastic moduli, but normally elastic moduli have lots of symmetries because they are derived from a free energy. Here, none of those apply. So we actually don't know if there are any symmetries in this weird fourth rank tensor, which is the polarizability tensor. That depends heavily on the protocol. So my short answer is the symmetries of the polarizability tensor can depend strongly on the kind of protocol. Now, the hope is there are classes of protocols that create similar polarizabilities, that not every protocol is different.
Thanks. And so the next question is from the public speaker we had this afternoon. So Shobendra Roy, please unmute yourself and ask your question.
Yeah, so I have actually a question. So so in electrodynamics, actually we can also construct a theory which is not only the global U1 gauge invariance but also local U1 gauge invariance.
Sure.
So does it have any correspondence to this granular system?
Yeah, so we do the local one when we have so that's the gauge principle, right? So so so, but here I'm not, so it's not just global gauge invariance here, it's local gauge invariance, but the local gauge invariance will show up when I put in charged excitations, right? I will couple to that. So yeah, so we are saying that that full local gauge invariant structure is there.
Okay, thank you.
Let me see if we have other. Yeah, so we have another question from Arpot Jyoti Maiti, who says that for the systems in the ensemble to satisfy the constraints, how can one actually form the partition function? Do you
Very good
use
question.
any main field approach or something?
Very good questions. No, it's not. It's not. So the assumption is, as in the frustrated magnets, that all states that satisfy the constraint are equally likely. This is the analog of the microcanonical assumption that we use in StatMech. Like if energy is conserved and then all states with the same energy are equally likely. Here, all states that satisfy the constraints are equally likely is the assumption. So when we have constructed, so that's a very good question. When we construct the stress correlations, etc., that is a basis of our constructing a partition function. That there is no distinction between states that satisfy the same set of constraints.
Right. And moving on to the next question, which is from Professor Ritoban Chatterjee. So, sir, please unmute yourself. Yeah.
Hello, Bulbul, can you hear me? This is Ritoban.
Hi, yes.
This is a very naive question that I have. I'm always kind of intrigued by this connection of properties between granular material and liquids. So I was wondering, I mean, if we take how liquids behave, particularly the motion of liquid, and then if we consider some sort of a limit where the particles are not molecules but much bigger and much heavier, is there any sort of situation where in this limit the behavior of the liquid will be similar to granular material? Is there any fundamental connection, or is it completely different?
Let me see if I understand your question, right? So granular materials can be flowing fluids also, right. But here I was more focusing on static granular assemblies. But what you're asking is if you take a normal fluid theory, right, and make the particles heavier and heavier, can I capture granular's physics?
That is exactly what I want.
Modulo the fact that friction, and I didn't emphasize this enough in this talk, but I because I didn't need to, that the friction between the particles is very, very important in determining these the properties. So in this, so in addition to making these things heavier so that you make them non-Brownian, right? That's what you're going to do. You're going to take a fluid and make the particles heavy. That means you're going to suppress Brownian fluctuations. That's certainly one of the ways of getting to granular. But then now if you start to make these particles, it could be that friction plays a huge role. Okay. But it doesn't have to. There are certain fluids which are just non-Brownian suspensions. But the kind of transitions I was mentioning at the beginning, this discontinuous shear thickening, it's now been shown conclusively that if you eliminate friction between the particles, this doesn't happen. You'll get a non-Brownian suspension, but you'll not have this feature.
Okay.
Maybe that helps a little bit?
Yes, very much. Okay. Thank you.
So the next question is from Professor Suchetana Chatterjee. So ma'am, please go ahead and ask the question.
First of all, thank you very much, Bulbul, for this fascinating talk. Now, are there questions from the YouTube users? Only then I can ask if there aren't other questions.
Right now, we don't have questions from YouTube.
Okay, so mine is also a very basic question. Now, in the beginning of your talk, you showed this I think, a video from something in Bob Berenger's lab, where
No,
was that a
was my
numerical?
lab.
Oh, that
That
was
was
your
my
lab.
lab.
Okay, that was your lab. Okay, so was that a numerical experiment where we had these particles and this thing is flowing, or is that?
Oh, you mean the Bob Berenger lab? What the photoelastic particles?
Yes, yes,
That's
yes.
a real
Can we?
experiment. I haven't shown you any numerical experiments in this
Oh,
talk.
that's a real experiment.
That's
That's
a
a real
real
so.
experiment. Yeah.
Okay.
Yeah.
Now, so I think the reason, because we saw these filamentary structures of these stresses moving, right? I mean, in a sense, the perturbations moving. Now, so being a cosmologist, that immediately gives me the picture of the universe, where we see, when we do cosmological perturbation theory, that's like sheer gravity. You know, there's no other interaction. There's just sheer gravity, and we do see structure forming in the universe in this filamentary way, and there are reasons for that. So is there any other, because here there are more interactions, definitely there are other interactions. We're not talking about gravity there probably, but can you tell us that why do we see this filamentary kind of structure? Because that's the same thing we see when we do cosmological perturbation theory. I was just trying to see if there is an analogy we can draw.
Yeah, no, that's a very intriguing question. And just to before I answer your question, there is this, the problem of clustering in granular materials is the same as the problem of clustering.
Absolutely same thing. Yeah.
So, but here the very basic physical reason for why you form filamentary structures in that particular experiment is quite geometrical. It's so I'm shearing, right? So I'm taking a rectangle and making it into a rhombus, or a square into a rhombus. So now I have a short diagonal and I have a long diagonal. Yes. And these particles are only respond to compression.
Yes.
So the force chains, or these contacts. So you start forming contacts in the compressive direction first.
Yes.
So you start off. So the nuclei of these kinds of structure formation are one-dimensional chains. Now, purely one-dimensional chains are never stable, right? And that's where you need friction, because if you have friction, you can have a zigzag chain.
Yes, yes.
And that's stable. So without friction, you would never be able to do this. But once you have that zigzaggy structure, the dynamics of how this develops is sort of this, that you keep compressing, right? You're shearing, so this diagonal gets shorter and shorter. So this zigzaggy structure actually buckles because you're compressing it. It's like taking a pillar and compressing it, so it buckles. But the system is dense enough that when it buckles, so if this grain moves out, it can actually make another contact, and that stabilizes it. So that's the microscopic process. So I think in a microscopic way, it's different from what you see, but but still an intriguing question. And that's why I think I'm saying, if you look at these kinds of emergent effective theories like ENM, where this is just, I'm not looking at the microscopic process of this creation, but saying it comes purely from the fact that I have certain conservation laws, then can we understand it?
Yes. So this is fantastic. Thank you so much for the answer, because I just want to make the point that the equivalence of friction in a cosmological scenario is actually the expansion of the universe. So that actually acts as an effective damping, like friction kind of term, and that is also responsible for the in the cosmological scenario. Like,
okay. So again,
expansion.
So I have to distinguish. We use friction very loosely sometimes. So there are two kinds of friction, and the suspension, the problem that I showed you, the two have to be distinguished, and they play different roles. One is, like, I have lubricated contacts. So I have contacts that have liquid between them, and there's friction in the sense that there's tangential forces. It's the transition from that kind of friction to solid on solid, rough, rolling friction that leads to this discontinuous
discontinuation. Yes.
So so again, I think, so it's a very, very intriguing idea that okay, so So that's a good point. Yeah, the fact that the liquid like friction is the can be mapped onto the expansion of the universe.
That's right. Thank you so much. Yeah, that's a
Okay,
fantastic thing. Yeah.
thank you.
Thank you, Professor Chakraborty. I don't see any further questions right now. So,
Can I,
uh,
sorry, Shagni,
yeah,
can I
sure. Yeah, sure.
interrupt you? I'm very intrigued by Bulbul's presentation of the part of her talk regarding the phase transition. You didn't go too much into that,
Right,
but you did talk about divergent susceptibility in the analog way. So,
right.
so I was wondering, is there also a generalization of the concept of critical exponents?
No, well, so this has been the struggle. So even like forget about a theory, even from experiments or simulations, which there are now many, many of, it's not clear if this is really a critical phenomena or a bifurcation, right? A straightforward bifurcation would show this too, in the sense that,
Right.
or like, right? They might. So, is there a diverging length scale? Is there a diverging? I don't know. It's been a complete, yeah. So there's so far nothing that has emerged as a diverging length scale in the problem.
But surely a stability, a Lyapunov kind of stability analysis would get you somewhere on that, wouldn't it? I mean, if it's a bifurcation.
If it's a bifurcation, yes, I don't. That hasn't been done. So there has been no probing of the critical exponents, even using a Lyapunov kind of argument.
Great. Thanks very
That's
much.
a good. That's a good actually. So I can. We hadn't thought about doing a Lyapunov analysis. Great. Thank you.
Thank you. Thank you very much, Bulbul.
Thank you, PSM sir, and thank you, Professor Chakraborty. So I think at this point we don't have any questions, and so if anyone has a question, I'm sure they can contact Professor
Yeah,
Chakraborty.
absolutely. Please
Yeah.
email me questions, comments. I would love to hear from you guys. And thank you so much again.
Thank you so much for joining us, Professor Chakraborty, from
And
this
I hope
different
to
time
join you
zone.
guys in person
Sure.
at not too distant future.
Yeah,
Take care,
hopefully.
everyone.
Yeah.
Okay.
So with that, we have a few announcements to make. Like we again meet tomorrow at 11. So this conference is mainly, as today morning it was said, that this is mainly meant for undergraduates to present their research work and to interact with their peers. The undergraduate portion of this conference begins tomorrow at 11 morning in Indian time, and then we are having from tomorrow and the day after we are having the undergraduate conference where we have about 20 talks in varying fields from astrophysics, cosmology to theoretical physics, condensed matter physics, and interdisciplinary sciences. And then we have posters as well in our website. Please join us tomorrow. We are eager to host you and through these talks. And also there has been an effort by some of the undergraduates in the Kolkata region, which I would please request Doi Payon to go ahead and share a bit of information with us about that effort. So please Doi Payon, go ahead and share the information.
Yeah, Shagnida, am I audible?
Yeah, you are.
Okay. So is my screen being shared? Hello?
Yes, Doipan, I
Yeah.
think we
Yeah,
can see
it
your
is.
screen.
Okay,
Yeah.
thank you. So first of all, thanks to Professor Chakraborty for that excellent talk and Precision team for conducting such an amazing, event in face of this lockdown and the pandemic situation. So since Precision always stands for undergraduate research and promoting undergraduate research and giving undergraduates this or graduate students this opportunity to present their work or the research that they're doing, in spirit of that, and of course presidency has always been a part of involving such things and promoting such ideas. So in spirit of that, me and my friends came up with the idea to utilize this pandemic situation and to create some sort of a society through which we can further this idea of research and self-development through a community sense. So we came up with this idea firstly within our local group of friends, then extended it to our nearest classmates, and then it drifted off from, and it just took pace from that, and we created this society, which is, as you can see on the screen, it's the student community of Indian physicists, which we have created to bring all of the students in India, or we are trying to bring other students from outside as well under a roof where we can present our research or our talks, or somebody who's interested in presenting something under a roof. And so currently we have a website ready for this. So of course we have a Facebook page as well and a YouTube channel that we have created to promote this, and we have been doing it since past 2 months, and we are at a number of 150 plus participants, members of the society. So the idea is as simple as the title or of the society, is to create a community of Indian physics students and to bring, of course, them together for this mutual development. So this is the website that you can see on the screen. And we organize weekly talks by members on various topics. So far, there have been talks on astrophysics, cosmology, theoretical physics, biophysics, condensed matter physics, and so on. We have conducted about 8 talks till now, and we want to further this idea. And of course, Precision is a great platform to promote this. So I would request everyone who sees this, please go to our Facebook page and please like it. And if you are interested, visit our website. And of course, you can see that there is the option of becoming a member. Or if you have any questions, just drop us an email and we will reply you back as soon as possible. So in the future, of course, the idea is a little far-fetched, but we want to have sessions or schools to promote the new kind of things that are coming up in physics, or the new tools that are required in physics in future. So we would like to really hold some schools or something like that in the future. That's the idea. So of course, we also have a magazine called Entropy. It's an online magazine where students who present their talks give a write-up, and it is presented there. And otherwise as well, people can include their write-ups. If they email it to us, we'll upload it. So this is it's been an initiative on our part to use this pandemic situation, because as you know, every dark cloud has a silver lining. So this is just a silver lining to what we can do to bring students, physics students, in under a roof and promote this idea of physics as in a broader sense. Thank you. Over to Shagnigda.
Thank you, Payan. So hopefully people will look into this and interact with you. And with that note, thank you, Professor Chakraborty, again. Thank you for joining us. Thank you, every participant.
Thank you very much.
Yeah, thank you to every participant who has been joining us again and again to make this event possible year after year. So yeah, see you tomorrow at 11. And yeah, have a good night or a good day according to your time zone. And yeah, bye.